Hey everybody, this is 7i Collisions here. So the scenario is the four cases below show four pucks viewed from above sliding to the right on a smooth table, so frictionless. Each puck collides and sticks to a rod. This is very important, sticks to a rod that can move or rotate with negligible friction. So no outside forces there. In all four cases, the pucks are identical. The rods are identical. The initial rightward velocities of the pucks are identical. And the initial velocities of the pucks are perpendicular to the rod's length. In cases A and D, the rod is fixed to the table by a pin with negligible friction. So these have pins right here, so they can rotate about those pins. In cases A and C, the puck collides with the center of the rod. So A and C hit dead on to the center here. All right, so first thing, and we'll reference this picture as we fill out this table, is they want us to determine whether the angular momentum is conserved in each case, linear momentum is conserved in each case, and kinetic energy is conserved in each case. So we'll put a X there if it's not, and a check mark if it is. Well, first off, let's do energy, actually. That's the easiest. Because it sticks to the rod, that is an inelastic collision. And by definition, energy is lost in an inelastic collision. So kinetic energy is not conserved in any of these. So what about angular momentum? Or let's do actually linear momentum first. We're sort of going from the bottom of the table up. So to conserve linear momentum, we need no outside forces. Well, the pin supplies an outside force in cases A and D. So there is an outside force there. So A and D will not have their momentum conserved, but B and C will because of that. So then last case here, angular momentum. So to conserve angular momentum, we need no torques, not no forces, but no torques. So when we look at these cases here, where we have the pin here, this pin, even though it exerts a force, it does not exert a torque because it's exerting that force at the point of rotation. So there's no lever arm, so there's no torque, so there's nothing to change the angular momentum. So all four cases, the angular momentum is conserved there. All right, next up, we are going to look at, it says rank the cases according to which of these has the most rightward linear momentum instantaneously after the collision to least rightward momentum, include greater than, less than, equal to signs there. So least rightward momentum, most rightward momentum over here, then justify your ranking. Well, as we said before, this is basically linear momentum. There are no outside forces in case B and C. So since there are no outside forces, they won't lose any of the system's momentum. So they've got just as much linear momentum afterwards as before. So they're going to have the most. So I'm going to put B and C over here, which is weird to put the most on the right. Just seems wrong to me. It seems like you put it on the left, but whatever. So B and C are going to be equal to each other, and they are going to have more than the others because they haven't lost any. Both A and D are going to lose some of their linear momentum. Well, A, when it hits here, it's just going to stick right there to the pin, and the pin's not going to allow this to move at all, and it won't rotate at all, so it's just not going to do anything. It's just going to stay right there. Whereas this one, it's going to continue to move instantaneously to the right. So this one will still have some rightward momentum. So D is next, and it is greater than C, which doesn't have any rightward momentum whatsoever. All right, and then last part here on this one, it says rank the cases according to most clockwise angular momentum to least clockwise angular momentum. So if we come back to our cases here in terms of changing the angular momentum, well, we need no outside torques here for this one. So in this case, remember, there's no outside torques on any of them. So they're all okay in that regard. Nothing's going to take away their angular momentum. But the difference here in this case is we need to recall that to get angular, whoops, that's not working. Let's try another color here. To get angular momentum from something that is going straight, we need to take its linear momentum times the distance from the pivot point. So let's look at that with reference to this. Well, this one doesn't have any lever arm. The puck's headed straight towards the pivot point, so this one does not have any angular momentum. Same thing with C here. C does not have any angular momentum. So when it hits and sticks to this rod, the rod's going to move off this way, but it's not going to rotate. So when we go to make this ranking, A is equal to C, and they are the least because they don't have any angular momentum. Then we look at these guys. Well, in each of these cases, the puck is still the same distance from the pivot point. So it's got the same mass, same speed, same lever arm there. So their angular momentums are actually the same. And since we won't lose any angular momentum, then they're going to remain their initial value. So B and D are going to be equal to each other afterwards there.